90 triangles. So, are you ready for definitions? You sure you don't want to look them up yourself? All right, well, we'll just do them together. Polygon is formed by I'm running out of room here, so I'm going to skip over here, 3 or more line segments. Basically, a polygon has to have straight edges. Does that make sense? It can't be curved, and they have to intersect at a vertex. That was the definition of a polygon. Let's wait for Claire.
Gosh, Claire.
All right, a polyhedron, that's a fun word, is a solid bounded by polygons. And those polygons are called faces. So I have a few here I can show you. Let me show you this one. So this would be considered a polyhedron. Can you see it? It's bounded by polygons, right?
Yeah.
And they're all triangles. Oh, the bottom fell out, but they're all triangles. So this is also one. It just happens to be a pyramid, but it's considered a polyhedron because it has polygons for its faces. Make sense? Okay. The edge of a polyhedron is a line segment formed by the intersection of two faces. So it's just a really long definition for an edge, right? An edge, okay? Make sense?
Yeah.
Just, yeah. The vertex of a polyhedron, where do you think that is? Yeah, where the edges meet. Vertex, 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 okay? So we could say a point where 3 or more edges meet. I'm guessing you already know what a regular polyhedron is. What do you think? All the faces are equal. It's basically the definition. All the faces are congruent regular polygons. Okay? Yes.
Does that include the base?
Yes. And we're going to talk about that. Okay? All right. A regular polyhedron, all the faces, because the base is a face. I know. All of the faces are congruent, regular polygons. This one's a little confusing, but I might show you the picture in the book. All right, a convex polyhedron. It says, if any 2 points on the surface of a polyhedron can be connected by a segment that lies entirely inside or on the polyhedron. It's going to be tight here, I know that. I'll show you what I mean on these here. So if I were to take a point, I don't know if this will show up, but I'll put a, no, not going to show up. If I put a point here and then on the other side here, and I connect my segment between those, is that going to be inside the polyhedron? Yeah. There's no place on this polygon that I could pick a point and another point where the segment connecting them will fall outside of the polyhedron. Does that make sense? Let me show you a picture in the book of one that does. That it would not meet this definition. Almost there. So this one right here. If you were to stick a point like, say, right here and right here and connect them, they would fall outside. That segment would fall outside of it. So that's not convex. It's called concave. Kind of caves in. That's how I remember it. It caves in. Cool? All right. Platonic solids. There's a fun word. Platonic solids. They are named, I'm going to give you the history first, a little bit. Named after the Greek philosopher Plato. Plato, Platonic. There are 5 regular polyhedra, and I'm going to show you which ones they are. They're on there's a picture of them on the next page of the notes, but 5 regular polyhedra. Let's look at them on the next page here, just so we don't have to list them all because they're in your notes. So I'm right here, the Platonic solids, aka regular polyhedra. These are the 5, and I can sort of explain why these are the only 5. Tetrahedron, 4 vertices, 6 edges, 4 faces. A cube, an octahedron, an icosahedron, and a dodecahedron. So let's first of all, tetra, what does that number mean? Does anybody know? Usually refers to what? The number 4, okay? Cube often refers to the number 6. Well, it is a 6-sided polyhedron. A cube is. Octahedron, how many sides do you think are in there? 8. Icosa, we haven't really talked about that. There's actually 20 sides here, 20 faces, it says right here. And then dodeca has 12 faces. Now, there's only 5 regular polyhedron for a reason. There's only 5 for a reason. Let me write this down here. The cube is sometimes called what's the word for 6 in geometry? Hexa. So sometimes it's called a hexahedron. So there's only 5 of them apparently because the sum of the measures of the angles, that meet at the vertex must be less than 360. And these are the only 5 that meet that definition for it to be a Platonic solid. So let me say that again. The sum of the measures of the angles that meet at the vertex must be less than 360. So that's the definition there. And I can write that here. Let's write it here. There's only 5 because the sum of the measures of the angles that meet at a vertex must be less than 360. And these are kind of new to me, so we're just kind of working with those. Almost done with definitions. And then the rest of it's pretty quick. All right. Cross section. I'm assuming you know what a cross section is. What do you think? Just slicing through a solid, right? Okay, so a cross section is the intersection, this is the formal definition, the intersection of a plane and a solid. So if I were to cut through this shape right here with a plane, what shape would that cross section be? Can you visualize that? Let me show you. Where'd the back of this go? Here. Okay, let's say I were to cut through this solid with a plane. So let's say my plane is down here on the bottom, and this thing goes longer. If I were to cut through it, it would make a triangle, wouldn't it? See what I'm saying? Okay, so for example here, this is not what we're working with today. These are, you get these in Algebra 2, conic sections. But if I took a plane and cut this through right here, it would form an ellipse. So this is the cross section right here. That's kind of what we're talking about. It's not really a hard thing to know what a cross section is, but I just want to show you some examples. All right. So here's a theorem you're going to work with. The number of faces, Euler's. I say it like the word oil. Euler's theorem. Okay. The number of faces, F, vertices, V, and edges, E, of a polyhedron are related by this formula. If you add the number of faces plus the vertices, it will equal the number of edges plus 2, always, in a polyhedron. Okay? All right. Turn it over. So this is what you're kind of going to be practicing today. Tell whether the solid is a polyhedron. If it is, name and find the number of faces, vertices, and edges. So does this meet the definition of a polyhedron? Is it formed by all polygons? Yes, it's formed by all polygons. It's considered a prism. Okay. How many faces does it have? 6. How many vertices? 1, 2, 3, 4, 5, 6, 7, 8 vertices, right? And how many edges does it have? I heard it. What do you think? Yes, 12. It's got 12. Now, let me just preface this by something. Some people have really good spatial reasoning. It's easy for them to look at this and know how many faces, how many edges, how many vertices. Others, they just don't have that. It's kind of hard for me. I have to count. I have to really look at it. So if you're getting it super quick, don't be frustrated with your friend because that spatial reasoning might be slightly different. So, all right. Is this one a polyhedron? Why not? Right. It's not made up of polygons. Okay, and this is a yes. They wanted us to say it's a prism. I don't really like that because we don't know for sure that the edges are congruent, but we'll just assume they are for this one. So we'd say it's a square prism or a cube. How many faces? 6 faces. How many vertices? 8 vertices and 12 edges. I'm abbreviating. All right. Doable, yes? All right. Find the number of edges of the wedge of cheese. Check your answer using Euler's theorem. All right. How many edges are on the wedge of cheese? 1, 2, 3, 4, 5, 6 on the bottom, 7, 8, 9. See it? 3 on top, 3 on bottom. Kind of looks like this. This one's just wider. This is a better wedge of cheese. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah? 9 edges. Now let's check it with the theorem. The theorem is faces plus vertices equals edges plus 2. How many faces are on this wedge of cheese?
5.
5. How many vertices? 1, 2, 3, 4, 5, 6. Edges is 9 plus 2. 11 equals 11. All right. Find the number of faces, vertices, and edges of the regular tetrahedron. Tetrahedron, that word tetra should say to you in your head 4, right? 4 faces. So F equals 4. Vertices equals 1, 2, 3, 4 as well. 1, 2, 3, 4. That's what this shape is right here, a tetrahedron. Okay. Edges, 6. So let's just check that it's true. Faces plus vertices equals 6 plus 2. 8 equals 8. Yes. All right. Turn it over. Or back, second page, however you want to look at it. Describe the shape formed by the intersection of the plane and the closed cylinder. So if I were to cut a plane through this, what shape would it be right there? A circle. It would be a circle. Okay? If I were to cut a plane down through a cylinder, here's a cylinder. If I were to cut a plane through it, what shape would it give me? It is a rectangle. It is. Right inside here is a rectangle. That's the cross section right inside there. Okay, if I were to cut the cylinder on an angle, what shape would it give me? Do you remember what I said here? It is an ellipse. Yes, it's an ellipse. It's like an elongated circle, and we call that an ellipse. Okay? Okay, here's a historical note. Are you ready? Carbon. Have you talked about carbon in science at all this year? Well, when you get to chemistry, you'll talk a lot about carbon. Carbon's in a lot of natural things. Carbon is an important element. Can you hold on a second? Thanks. Up until 1985, only 2 forms were known. The crystalline version diamond. A diamond is made up of crystallized carbon. It's the hardest substance known to man. The other form of carbon is graphite, which we know where is that in our everyday. Pencil lead. Then in 1985, scientists at Rice University discovered a 3rd form of carbon. It's called carbon-60, known as Buckminster fullerene. Yes. Buckminster Fuller, right here, is an actual person. He's known for his architecture. Okay, Buckminster fullerene or buckyball. These guys were awarded the Nobel Prize in Chemistry in 1996 for their discovery. The buckyball is 60 atoms of carbon joined at 12 regular pentagons and joined as 12 regular pentagons and 20 regular hexagons. Right here, the soccer ball. Have you ever looked at a soccer ball closely? The shapes here, there's a hexagon, there's a pentagon. Okay. The pattern on a soccer ball shows the structure of a buckyball. Imagine 1 carbon atom at each vertex on the soccer ball. You will never look at a soccer ball again the same. All right? This is a buckyball. Say that next time you're playing soccer. So this is actually what the C60 carbon looks like, carbon-60. The most famous geodesic dome, this was designed by Buckminster Fuller, and it's made up completely of polygons. And it's a very strong structure. Do you know where that is? Disney World. Yes, Buckminster Fuller. Okay? So this is just kind of a historical note. There is application to this stuff, and you're going to learn a lot about carbon in chemistry, I'm sure. All right, where is a very prevalent carbon atom that you guys know of? Do you know? Other than diamonds and pencil lead. Yeah, would we be able to breathe without exhaling something? What do we exhale? CO2, don't we? Yes, carbon dioxide. So